Hi everyone, welcome to another online review session for Math 111. This week we will be covering just one quiz, quiz 12, deals with polynomials. So what I did, I think there's three different problems or three different sections in this review. The first one, I kind of just wanted to give some general information, just talk through some stuff. Sometimes it helps to see stuff, not always in examples, but more in a general form. So with polynomials, there's a few things you need to know, but I think the most important are these first three, the end behavior, the Y-intercept, and the X-intercepts. So for the end behavior, there's really four different possibilities. So, okay, what I'm saying is if you have a polynomial like, for example, say f of x equals 5x to the third plus 2x squared minus 7x minus 11, for example. You can determine the end behavior of this polynomial just by looking at one term, just by looking at the term with the largest degree. So really, all you have to do is look at this thing here. And it tells you everything you need to know about end behavior. There's four different possibilities, all of which you can get from here. And so what you need to do is look at both the leading coefficient. So maybe I'll write that up here, leading coefficient. And it's either going to be a positive number or a negative number. In this specific example, it's a positive number because this 5 right here is positive. But it could also be a negative number, like negative 11x to the 5th power plus 7x to the 4th minus 2x plus 6. Sure, whatever. Negative leading coefficient, positive leading coefficient. The other thing that you have to look at is the degree of the polynomial. And you determine the degree of the polynomial by looking at the exponent, looking at finding the largest exponent in the polynomial. So again, you're just looking at this first term here. In this case, the degree is 3. In this case, the degree is 5. And what you need to determine is whether the degree of the polynomial is an odd number or an even number. And what that gives you is all four possibilities. So an example of a positive leading coefficient with even degree would be something like x to the 8th, sure, minus 3x to the 7th plus 11x squared plus x, sure, there's a polynomial. And the degree is even because 8 is an even number, and the leading coefficient is positive. It's positive 1 in this case. But if we had negative 3x to the 4th plus 2x squared minus 11, then the degree would be even, leading coefficient negative. Anyways, here's the four different cases. Really all you're looking at is this term. It gives you your end behavior. For end behavior, well, describing it is one thing. Really what we're saying, let me scoot this over to the side, is we're trying to figure out, and polynomials do a lot of weird stuff in the middle. They go up and down, they cross axes, they have all sorts of weird shapes. But if you go far enough to the right or far enough to the left, one of four things happens. Either it goes up when you go to the right and down when you go to the left, or it goes down when you go to the right and up when you go to the left. Or I suppose it could go up when you go to the right and up when you go to the left. And finally, it could go down when you go to the right and down when you go to the left. So these are only four possibilities of what could happen for end behavior of polynomials. It turns out you can figure out which case you're in just by looking at the degree and whether the leading coefficient is positive or negative. One way, if you don't want to memorize all four of these scenarios, you can start by just looking at the leading coefficient. If it's positive, that means you go up when you go to the right. Note we're up to the right in both of these cases. And then what you do is you look, and if it's negative, you go down when you go to the right. So if it's positive, up to the right, negative, down to the right. And then what you do is you look at the degree. If the degree is odd, that means you go the other way when you go to the left. So we went to the right, we went up when we went to the right, so we must go down when we go to the left. We went down when we went to the right, so we must go up when we went to the left. Or if the degree is even, then you go the same way. We're going up this way, now we'll go up this way, down this way, down this way. Really, I think what's most important is being able to come up with this picture and have a conceptual understanding to write this, it looks kind of confusing. But what I hope I can show you is this isn't nearly as bad as it seems. So the way you describe this in behavior is you say, as x goes towards infinity, y goes towards infinity. And as x goes towards negative infinity, y goes towards negative infinity. All I'm saying here is that as x goes to infinity, I'm saying when I go to the right. X goes to negative infinity when I go to the left. So if I'm going to describe the end behavior, I have to say what happens when I go to the right and what happens when I go to the left. Well, y goes to infinity means up. So when I go to the right, I go up. Y goes to negative infinity means I go down. So when I go to the left, I go down. So if you keep that same idea, we can answer all these questions. As x goes to infinity, that's saying when I go to the right, it's supposed to be an infinity sign. Looks like I go down in this case when I go to the right. So y would go to negative infinity. And as x goes to negative infinity, in other words, when I go to the left, looks like I'm going up. So y goes to positive infinity. And similarly here, when you go to the right, it goes up. And when you go to the left, goes up. Just describing this picture right here. This one, when you go to the right, it goes down, left, it goes down. Okay, so then as x goes to infinity, y goes to negative infinity. Right, down. X goes to negative infinity, left, also down. And behavior. You get it all just by looking at that first term, the coefficient and the degree. And if you can get the picture, that's good. But being able to write it with the right notation it's important for calculus to be able to write this. This idea of limits is really a calculus idea. So that's why they're kind of introducing it to you now in this pre-calculus class. All right, the rest of the topics won't take as long as that. I think that's the longest general thing. Y-intercept. What you need to know about the y-intercept is it happens when x equals 0. If you're thinking about a graph, this is the y-axis right here, this vertical axis. So, sure, there's a graph. If I want to know when it crosses this y-axis, this point right here, well, the property that this point has is that its x-coordinate is 0. The left-right is 0 right here. So all I got to do is make my x-coordinate 0 and figure out what y is, and that'll give me the y-intercept. In other words, all you got to do is evaluate f of 0. Take your polynomial, change all the x's into 0, see what you're left with. That's the y-coordinate of your y-intercept. X-intercept, very similar. Same thing. Draw a polynomial. Pretty similar to the one I drew before. X-intercepts are where they cross the x-axis. This horizontal axis is the x-axis. So I got one here, 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 and here. I got 5 of them in this case. Actually, I don't like that. So I want to redraw this so I can illustrate 2 different concepts. So I'm going to redraw it a little bit different. We got x-intercepts 1, 2, 3, 4. So x-intercepts happen when we cross the x-axis. They happen when y equals 0. A point that I want to make is that you will always have a y-intercept. We're always crossing this axis. You may not have any x-intercepts, or you may have multiple like we got here. They happen when y equals 0, so what we have to do is solve f of x equals 0. In other words, take your polynomial, set it equal to 0, and solve. And all the solutions will be the x-intercepts. One other comment I want to make on x-intercepts, and we'll do examples of these as we go on, is about multiplicity. The multiplicity is, very informally, is how many times the x-intercept appears when solving. That might make no sense now. I think when we actually do an example, you'll see what I'm talking about. That you can get solutions, the same number that happens several times when you're solving this equation. If multiplicity is even, this is going to be very informal again. Graph ounces. The hell am I talking about? Looking at these 4 x-intercepts. In this case, the graph just went right through that point. Similarly here, it went right through. Similarly here, it went right through. Not here. Here it kind of hits the x-axis and then it turns around and sort of bounces off. That means that we have even multiplicity. For this root here. We got odd multiplicity for all the rest of them. If this seems a little bit vague, it is. Don't worry, we'll do examples, and I think these concepts will be a lot clearer. But I wanted to start out just talking about things in general so that I can come back and reference this page as we go on throughout this review session. All right, so let's actually do some problems. Here's a polynomial much neater than the ones I drew. It says, consider the polynomial graph below. A, is the degree of this polynomial even or odd? It's a good question. Well, we can figure this out just by looking at the end behavior. We look at looks like it goes down when we go to the right and up when we go to the left. So if we go back to our end behavior charts, down when we go to the right, up when we go to the left. What it's telling us is that the degree is odd. And by the way, the leading coefficient is negative. Okay, is the degree of this polynomial even or odd? Look at the end behavior. It's odd. It's odd because it goes in different directions when it goes to the left and when it goes to the right. It goes down here, it goes up here. Is the leading coefficient positive or negative? Again, look at in behavior. As we already alluded to, we're in this case here. And this case corresponds with a negative leading coefficient and an odd degree, which we already talked about. It's negative. Because it goes down when it goes to the right, it's negative. Up when it goes to the right, it's positive. What is the value of the constant term? Okay, that's kind of a tricky question right there. Really, it turns out that what this is asking for is what is, maybe AKA, what is the Y-intercept? The Y-intercept will always be the value of the constant term. Why? Well, look at a polynomial like this. The way we figure out the Y-intercept is it happens when x equals 0. So imagine this polynomial right here, if I made all the x's 0. This would be 0, this would be 0, this would be 0. And then I'd subtract 11. So the y-intercept is at negative 11. But there's nothing special about this polynomial. That always happens. When you make x's 0, all of the terms will go away except for the constant term. So whatever the value of the constant term is will always be your y-intercept. That might be worth writing. The y-intercept is always the value of the constant term. So therefore, if I go over here, my y-intercept, it looks like it's at 3. My y-intercept is at 3, so the constant term has a value of 3. The negative 0 occurs where? Okay, zeros are another word for x-intercepts. That's important. So x-intercepts go by zeros or by roots. There's subtle differences when you get into different levels of math. For our purposes, those three things are synonymous. 0, x-intercept, and root all mean the exact same thing for our purposes. The negative 0, okay, so we have an x-intercept right here and right here. And so it's referring to this one. It says the negative 0. This 0 is at negative 2. This one is at positive 3. So talking about this one, the negative 0 is the multiplicity even or odd. Well, note that the graph right here, it bounces. Right? It bounces off at this point. It doesn't go right through, it bounces off. We talked about earlier that if the multiplicity is even, the graph bounces. So the negative 0 occurs where? It's right here. X equals negative 2. Is this multiplicity even or odd? It's even, because it bounces. Put bounces in quotation marks because that doesn't feel like a very mathy word. I don't know if your book used that word, but it describes what's going on. It's bouncing. It doesn't go through. The positive 0 occurs where? Okay, here's our only other 0. This one's a positive number, 1, 2, 3. Occurs at x equals 3. Guess that's a question. The answer is 3. Is its multiplicity even or odd? Well, since the graph goes right through this point, the multiplicity is not even, therefore it's odd. It doesn't bounce. What else can you get from a polynomial? I mean, you can answer all these questions. It turns out that you can come up with the equation of the polynomial, which is kind of crazy that just by looking at the graph, you know it. And what you do, what is the equation of this, I lied, of this third degree polynomial? It has to tell you that's a third degree polynomial. But if it tells you that, then we can answer these questions. And the way we answer them is we say, all right, it had a 0 at -2. So what that means is x plus 2 must have been a factor of this polynomial. If I factored this polynomial all the way out, x plus 2 must have been one of the factors. And the reason that's true is because the way I came up with this answer -2 is I set my polynomial equal to 0 and solve. Right, we talked about that up here. The way you find the x-intercepts is you set your polynomial equal to 0 and solve. So if I ended up with -2 as an answer, I must have had x plus 2 as a factor. Because x plus 2 equals 0, solve that equation and get x equals -2. If -2 is a factor, sorry, if -2 is a root, x plus 2 is a factor. If positive 3 is a root, x minus 3 is a factor. However, this is not the polynomial in its factored form. And the reason why is this root has even multiplicity. By even multiplicity, I mean that that factor showed up twice. So earlier when I talked about multiplicity being how many times that thing appears, you're like, I have no idea what you're talking about. What I meant was this thing. When you factor it all out, you'll actually get 2 of these x plus 2s. So when you go to solve it, you'll get x equals -2 from this one and another -2 from this one. That's why it has even multiplicity. I knew that there were only 2 as opposed to 4 because it's only a third degree polynomial, so I can only get these 3 factors. You're like, all right, so this is my answer. Not quite. We have to make sure not only our x-intercepts match up, but also our y-intercept. We have a y-intercept at 1, 2, 3. The catch is that there might be a number out in front of this entire thing. There could be a number right here. Maybe I'll put A to represent the number. Might be. It might just be 1 and we don't need it, but maybe it's a number. We have to figure out if there's a number here. A number here won't cause any roots because that number is never equal to 0. It's just these that turn into zeros. So we can't get them just by looking at the x-intercepts. But the y-intercept, to figure out the y-intercept, you make all the x's 0. And we know that the y-intercept is supposed to be at 3. So what I'm saying is when I make all these x's 0, y-intercept 0, 3 is on graph. In other words, when x equals 0, y should be equal to 3. So a times 0 plus 2 times 0 plus 2 times 0 minus 3 has got to be equal to 3. -12a has to be equal to 3. A must be equal to -1/4. So the equation of this polynomial is it's -1/4 times this factor times this factor times this factor. Like, that doesn't look like a polynomial. Well, it is a polynomial. It's just in the factored form. If you really want to FOIL everything back out, you could. You don't have to. It's perfectly fine. It's an equation. It's a polynomial. It's just in the factored form. Call this right here the final answer. On the quiz, I don't believe you have to come up with this. I think you have to choose this from a multiple choice list. So I don't know if you need to be able to solve it quite as in-depth as I just did, but you could. But really what you can do is be like, well, this multiplicity has to be even, so there must be 2 of these. This one has to be odd, so there's 1 of these, and kind of work your way, process of elimination, figure out what the answer is. All right, moving on. I think the third and final problem is the one that I consider the most interesting. So first one was just talking generally speaking. I mean, just a good guide for you to have. I've memorized this end behavior stuff. It's not too bad to memorize. I memorized the pictures and how they show up, and then I can back into this notation. And you can do whatever you want. Definitely memorize how to get the y-intercept. It's easy. It's 3 points. Remember how to get that. X-intercepts can be hard, but you should know how to find them and understand what multiplicity means. And then know, all right, what if you start out with the graph? Because that happens on a quiz. On the quiz, they'll give you the graph and ask you a bunch of questions about it. One way they can ask you questions is by giving you the graph of the polynomial, asking you all about it. They can ask you many of these same questions. They just give you the equation of the polynomial. So that's what we're doing in this last problem here. You'll see that these questions are very similar to the questions we had up here. The difference is now we don't have the graph, we just have the equation. So I'll show you how to do it. So the first one, list all possible rational roots of this polynomial. Okay, that's a little bit tricky. There's this thing called the rational root test. And what the rational root test says is that all possible, so not all roots, remember roots are the same as zeros are the same as x-intercepts. Not all roots, but all of the possibilities, the things that could be them, and not really all roots, but the rational ones. So what I mean by rational are numbers that can be written as fractions. So not the square root of 2, but 3/7. All possible rational roots are of the form P over Q. Weird. You know what? I'm not going to write it that way. I think there's a better way to write it. Are of the form, and it's an integer factor of the constant term. Divided by integer factor of the leading coefficient. Why? You can talk yourself into why the rational root test works. Actually, I think it's kind of cool why it works. You sort of look at roots and think about, well, where's this 3? If I FOILed everything out, where would it end up in my polynomial? It's kind of confusing, but you can get at the rational root test. It really does make sense. If you have the time to sit down and learn why this works, it's interesting. I mean, maybe it's a 15-minute lecture or something. I think for our purposes, I'm going to skip it and just tell you that this is the punchline. Hopefully in your book they teach you why this works. If you're ever curious, I can make a video showing you why it works, because really it is interesting. But all you need to know for the quiz is that it works, not why it works. So, constant term, I'm talking about this 3 right here. Integer, I mean whole numbers. So the whole numbers that divide evenly into 3 are just 1 and 3. Okay, that's not entirely true. It's plus or minus 1 or plus or minus 3. You know what I'm saying? Like negative numbers or positive numbers. We're going to end up with negative numbers and positive numbers on all of these factors. So I'm just going to put a plus or minus out in front. We'll take care of those later. The only integer factors of the constant term are 1 and 3. The only integer factors of the leading coefficient are 1 and 2. Yeah, plus or minus 1, plus or minus 2, but I took care of the plus or minus over here. There could be lots of possibilities. 3 and 2 are both prime numbers, so we don't have that many. But imagine if this were a 6. Then 1, 2, 3, and 6 would all be integer factors of this. But it's not a 6, it's a 3, so just 1 and 3 work. And so what you have to do is figure out all the possibilities that you come up with by taking one of these two numbers and dividing it by one of these two numbers. Oh, and then make them all plus or minus. 1 divided by 1 is just 1. 3 divided by 1 is just 3. 1 divided by 2 is 1/2. And 3 divided by 2 is 3/2. In this list of 8 numbers, these are the only possibilities for rational roots of this polynomial. It's a third-degree polynomial, so it has at most 3 rational roots. But it might have as little as, it might have none. We'll never have one. Not in your purposes, because we're going to have to use these. But on the quiz, it could have as little as just 1. Maybe just 1 of these work. Maybe 2 of them work. Maybe 3 of them work. Is that true? Maybe only 1 or 3 are the only possibilities for how they work. Anyways, here's all the possibilities. List them, plus or minus 1, 3, 1/2, 3/2, call it good. Why is that helpful? I mean, it's not telling me that these are roots, it's just telling me that they're possibilities. So that's not really helpful unless we have a method of checking which one of these actually are roots, turning them from possibilities to actual numbers. If we do, that's what part B is getting at. So part B says test to see if x equals 3 is a 0 or a root. Remember, roots and zeros are synonymous of this polynomial. The way you test it is, let's go back up here. If 3 is a 0 of a polynomial, zeros are synonymous with x-intercepts. What that means is that 3 is an x-intercept of the polynomial. If 3 is an x-intercept of the polynomial, like it is in this picture right here, what that is saying is that when my x-coordinate equals 3, the height is 0 because it's going right through the x-axis. So what that is saying is that the point 3, 0 is on the graph. Test to see if x equals 3 is a 0. If it is, 3, 0 is on the graph. How can I figure out if 3, 0 is on the graph? Well, all I got to do is change all the x's into 3's and see if it's equal to 0. Figure out f of 3. Does f of 3 equal 0? Question mark. Well, let's see. F of 3 would be 2 times 3 cubed minus 25 thirds, sorry about the fractions, times 3 squared plus 6 times 3 plus 3. This thing equals 0? I can't tell. 3 cubed is 27 times 2 is 54. This doesn't look like this is going to work. Maybe it'll work. We'll see. Oh, it'll work. 3 squared is 9. 25 thirds times 9. This is 9 over 1. So you can cancel out the 3 in the denominator with one of the 3's that make up the 9. And what you're left with is minus 75. 25 times 3. And then this is 18. And this is 3. 54 and 18 is 72. Plus 3 is 75. Minus 75 is 0. Test to see if x equals 3 is a 0 of a polynomial. Yes, it is. The reason it is because 3, 0 is on the graph. I know 3, 0 is on the graph because when I change all the x's into 3's, my y is equal to 0. So I found one of the zeros, one of the roots, one of the x-intercepts. But there's 2 more, and there might be as many as 2 more. So I got to do this again? No, you don't want to do this again. You only want to do this method to find 1 0. Just find one of them. You'll be able to factor to find all the remaining ones. So the way you factor is by doing, well, there's a couple of different ways you can do it. You can do it using polynomial long division, or you can do it using synthetic division. I like polynomial long division better. I think your book uses synthetic division. Either method's totally fine. I'll work out polynomial long division so that you have the options of which ones you do. So I have this polynomial, f of x is equal to 2x cubed, I got it right here, minus 25 thirds x squared plus 6x plus 3. I don't like fractions. It's not really true, I don't mind fractions, but I assume you don't like fractions. You can get rid of all the fractions by factoring out the least common denominator. In this case, the only denominator I have is the 3. So if I pull 1/3 out from this entire polynomial, I can make it not have any fractions. That would turn this 2 into 6, this 25 thirds into just 25, this 6 into 18, and this 3 into 9. If you don't know where I came up with those numbers, if you took this 1/3 and distributed it all the way back through, 1/3 times 6 is 2, 1/3 times 25 is 25 thirds, 1/3 times 18 is 6, and 1/3 times 9 is 3. So essentially, what I'm doing is I'm taking each of these things and I'm dividing them by 1/3. 2 divided by 1/3 is the same as 2 times 3. That's where this 6 came from. Anyways, I think it's easier to not have fractions, so I like to first get rid of the 1/3 and then factor this thing out. To factor that thing out, I know that 3 is a 0 of this polynomial. If 3 is a 0 of this polynomial, then x minus 3 must be a factor of this polynomial. So if I do x minus 3 divided by that polynomial, 6x cubed minus 25x squared plus 18x plus 9, it should divide in evenly. Because it's a factor of the polynomial, it's got to divide evenly. It should get no remainder down here. So either synthetic division or polynomial long division at this point. If you know polynomial long division, you want to get rid of this 6x cubed column. When you get rid of 6x cubed, you should put a 6x squared up here. Change color so it doesn't run together as much. Throw a 6x squared here because 6x squared is what I'm going to multiply by x minus 3. 6x squared times x gives me 6x cubed. 6x squared times negative 3 gives me negative 18x squared. And now I do subtract. 6x cubed minus 6x cubed, that goes away. Good. Every single iteration of this one column should go away. Be careful here. It's really tempting to write 43x squared or negative 43x squared or something. You're subtracting. Negative 25 minus negative 18 is the same as negative 25 plus 18. Minus a negative is the same as plus. Negative 25 plus 18 is negative 7x squared. Number one spot people make a mistake is right here. They don't get this number here. You're subtracting. You're always subtracting each iteration. So, okay, now I want to repeat. Exact same process. I want to get rid of this negative 7x squared. To do so, I needed negative 7x up here. Negative 7x times x gives me negative 7x squared. Negative 7x times negative 3 gives me positive 21x, and now I subtract. This column goes away. Good. I should lose a column with every iteration. 18x minus 21x is negative 3x. Again, we're subtracting here. This isn't 39x. You don't add these, you subtract them. We'll get rid of this negative 3x. Better put a negative 3 up here. Negative 3 times x is negative 3x. Negative 3 times negative 3 is positive 9. I subtract, I get 0. That's a good thing. You want to get no remainder. Because if you get no remainder, that tells you that this polynomial right here is just x minus 3 times 6x squared minus 7x minus 3. And don't forget, you still have this 1/3 out in front. So now I have it as a linear term and a quadratic term. So what I got to do is I got to factor this quadratic term. I need some room for that. Let's factor 6x squared minus 7x minus 3. Leading coefficient is not a 1. So there's a couple different ways you can factor this. The method I use is kind of long. It's a lot of steps, but it removes the guess and check aspect of the method that most people use. First step, find two numbers that multiply to negative 18 a times c and add to negative 7. So multiply to negative 18 and add to negative 7. Negative 9 and positive 2 are the two numbers that multiply to negative 18 and add to negative 7. Step 2, once you figure out negative 9 and positive 2, is replace negative 7x with negative 9x plus 2x. So leave the 6x squared alone, leave the minus 3 alone. Just replace negative 7x with negative 9x and plus 2x. And again, the negative 9 and the 2 came from finding two numbers that multiply to negative 18 and add to negative 7. We're not done here. We're not factored. We've just turned it into something that has 4 terms, which we can now factor by grouping. Greatest common factor from these first two is 3x. Pull out a 3x, you're left with 2x minus 3. Now you look at these next two. You want to be left with 2x plus 3, but you got to pull something out. Well, I already have a 2x plus 3, so let's just pull out a positive 1 as a placeholder. Now I got two terms that both have a 2x minus 3 in them. So I'll factor that out. You get 3x plus 1 left over. What I'm saying is this polynomial factors to 1/3 times x minus 3 times 2x minus 3 times 3x plus 1. And now that I've factored it all the way out, I can find all of the zeros by setting each of these 4 things equal to 0. 1/3 equals 0? That never happens. There's no x's that are in here that will make this thing equal to 0. No solutions. X minus 3 equals 0. Add 3 to both sides, you get x equals 3. This is 0. 2x minus 3 equals 0. Add 3 to both sides, divide by 2. You get 3/2 is 0. 3x plus 1 equals 0. Subtract 1 from both sides, then divide by 3. You get negative 1/3. So here's my 3 zeros. Here's the factor form. Finally, sketch an approximate graph of that. They're going to give you graphs and have you choose which one is right. So that'll make that a little bit easier for you. But if you were doing this problem, okay, we want to make sure we have the y-intercept. If all the x is 0, we have 3. 1, 2, 3. So better go through this point right here. My zeros, I got a 0 at x equals 3. 1, 2, 3. And at 3/2, right in there. And at negative 1/3, so right here. So that's negative 1/3. Maybe it should be a little bit more over there. Whatever, good enough. In behavior, you could figure it out if you want to, but actually, we don't need to. Because to go through this route, and then go through this one, and all these multiplicities are odd, they're all just 1, all of these factors showed up one time, means I need to go through the graph at each of my x-intercepts. Nothing bounces off. So it must start down here, go through this guy, turn around, shoot off that way, shoot off that way. How do I know how far down to go here? You don't know. You figure out how far down to go in the calculus class, or you can put in that x value to figure out the y value from the equation. But for our purposes, you don't need to. Just get one that looks something like the right answer. Because you'll have multiple choice, you'll be able to use process of elimination. So just make sure that the one you choose has the right end behavior, the right y-intercept, the right x-intercepts, and the proper multiplicity of those x-intercepts. Through the graph in all three, I didn't bounce off in any of them, because all of these multiplicities were odd. The multiplicity is 1 in each of these cases, because each of these factors only showed up one time. If this were x minus 3 times x minus 3 times 3x plus 1, then I'd have a multiplicity of 2, which showed up twice. But I don't. These are all different. 3 roots, each with multiplicity 1. Oh, that's everything I got on polynomials. So maybe I'll cut it off there. Hopefully that works for people. I'm going to come back up here and leave this as the last screen. So you can pause the video and write this down if you had trouble copying it down when we were working on it.